Okay, so now we can look at our horizontal or slant asymptotes. So we knew our denominators gives us our vertical. So how do we create the horizontal and slant, or how does the function create it? And what we have to do is look at our polynomials in this way. And so what we have is a top degree and we have a bottom degree. We have a polynomial on top and a polynomial on the bottom. That's what makes our rational expression. So you're going to have this polynomial here and this polynomial here. So let's look at our first one. If you notice here, the degree of the two polynomials are the same. So as we keep plugging numbers in to our function, see, I got a 4, and then I'm going to plug in 100. Well, let's just go for it. And we plugged in 10 billion. And what does it become? It's not really 2/3. It's just really, really close, but the calculator errored out and just says close enough, 2/3. So if you look at our leading coefficients, what are they? It's 2/3. See, what's happening is as this gets bigger and bigger, this stuff starts to disappear. Because if you were to take 1,000,000 and square it, and then add another million, well, I'm sorry, but if you have 1,000,000 squared, $1 million is nothing to you. Just put it this way. Let's make it even smaller. Let's just say that we take $1,000 and square it, and then we add to it $1,000. Well, $1,000 squared is 1, 2, 3, 1, 2, 3. It's $1 million. If someone says, hey, I'll give you $1 million, you know, I just want you to add an extra 1,000 to that. No, it's so freaking huge that this doesn't matter anymore. If you said I got $1 million and $1,000, you would just say I've got $1 million. And now if you make that billions, think about it, we're going off to infinity. This would be 1 billion squared plus 1 billion. That's 1 billion billion. It's huge. So what's happening here is these numbers, as x approaches infinity, as our x keeps getting bigger and bigger, these just disappear. And you end up with this as what's happening. So at the very, very end of this, what we are getting is y equals 2x squared over 3x squared. And so what happens to the x squareds? They just cancel away. You're getting like 1 billion over 1 billion. They just cancel and give us 2/3. So long story short, that was really long. All you have to do is look at the leading terms. If the top degrees are the same, then we're going to get 2/3. And we can carry this down through all of them. So we're just looking at the leading terms. The rest of it doesn't matter when we're talking about our horizontal asymptote. So this would be y equals 2/3, which means our horizontal asymptote 2/3 is right here at the 2/3 mark. Right there at 2/3, like that. So let me show you this in Desmos, and you can see what I'm talking about. So right here, you can see we have the same degree. I've got an x squared on the bottom, x squared on the top, same degree. So all of this is just basically going to disappear here, leaving us with 5x squared over 2x. And you can see there is our horizontal asymptote. So if I change the numerator, now it's 2 over 2, that's 1. So you can see now it's at y equals 1. So the bottom numbers, and what if we go negative? Oh, there you go. Negative 2 over 2 would be negative 1. That would be negative 2/5. See? So whatever these two leading terms are, right? Whatever the leading coefficients are, that is your y equals horizontal asymptote. And what does that mean? Well, let me make this into 4 over 2. So 4 over 2 is 2. So now we're at 2. So what that means is as this approaches infinity, see, we're getting smaller. It's already getting close. You can zoom in and see right here, it's getting close to the graph. So as we approach infinity, our line is just getting closer. Our rational function is getting closer and closer to this line y equals 2. So it's getting closer. It's never going to actually hit it. It just keeps getting closer and closer. Well, it could hit it, but if it does, it'll hit it and then come back up from below, which we can test later. But so it can cross this, but it's getting closer and closer. So as we approach infinity, it's going to get closer and closer and closer to this line. So you can think, oh, it looks like exactly the same. Now, if we scroll in, to really scroll in a lot, you can see there's a slight separation there. So it's approaching this y equals 2/3. So that's why we draw this line. And it works the other way as well, see? So whatever those two leading coefficients are, that is what our y equals will be, see? As I move it, that's 2/3, that's 4/5. See, y equals 4/5. It's just those two numbers together. So that is how we get the horizontal if the degrees are the same. All right, now what happens if the top degree is smaller than the bottom degree? So the bottom is bigger than the top. Well, this goes off to 0. Let's see that one. So here you can see that we have x squared. So that means our bottom degree is larger than our top. Our top is smaller. So you can see now here, no matter what I do with my a, if I move my a up and down, all it's doing, remember, if you make the a bigger, it vertically stretches. So all it's doing is vertically stretching our function, but this is still 0. It doesn't change. Even the b will not change it, see? It doesn't matter what I have for my a and b. This is always going to be 0. So why? Why is that the case? Well, think about it again, the way we're talking. If we look at just this would disappear and this would disappear, right, as it gets bigger. Then we would end up with y equals 2x over x squared, and then that would cancel to give us 2 over x, right? So this is what we're actually getting. So as our x approaches infinity, that's what we're getting. Well, this is 2 over x. This is a fraction. So what we're getting here is like 2 over 4, 2 over 100, 2 over 1,000. And then at the very beginning, at the very end, it's 2 over 10 billion, right? So 2 over 10 billion is extremely small. This is approaching 0. The fraction is getting smaller and smaller and smaller and smaller. And so if you look at our graph, you can see it's a fraction here. Right here, it's becoming more and more of a fraction. We are talking about an actual fraction. So our fraction is just getting smaller and smaller and smaller. And so what is our fraction approaching? 0. So eventually, it's going to just keep trying. Not eventually, I'm never going to hit 0. Again, it could cross, but it's approaching it. It's getting closer and closer. So no matter how far I scroll out, all right, if I go way out there, it's going to take me a while to get here. Let's get really far out there. Okay, so like 7,000, right? That would be plugging it in. So that would be 3 over 2 times 7,000. So now if you scroll in, it's like a microscope. See, we're looking, like zooming in now here. So you can see there's still a gap. So even though it looks extremely close, it's approaching 0. You can even see, look how close, small that is. See, it's super small. So you can see our fraction getting smaller and smaller and smaller. So if you look at it as a decimal, see our decimal is shrinking. Now we're at 0.61, 0.5. Say 0.03, and as I keep scrolling out, you're going to see it's approaching 0. So whole idea is if the bottom degree is bigger, we're going to get 0. And so to do that for your graph, just put little dotted lines on the end, and that would be your horizontal. Okay, we got one more. So top degrees are the same. Degree and top and bottom are the same. Top degree is smaller than the bottom. We go to 0. Now what happens if the top degree is larger than the bottom? Well, what we end up getting is what's called a slant asymptote. So if you were to take this and simplify it, right? Again, that would just disappear. And so we get y equals x squared over x. And that's just x. See, we would get y equals x in this case. Sort of. You're going to see what we get. But this goes off to infinity is the whole idea, or it will go off to negative infinity. We're getting a linear equation here. So what we want to do is take this numerator and denominator and actually divide them. So we're going to take x squared plus 2x and divide it by x minus 1 to get a new simplified equation. So we're going to use synthetic. We get 1, 2, and then there is no constant, so 0, dividing by 1. So we bring down 1, multiply 3, we get 3. And again, this is our remainder. So what this would really be is plus, right, 3 over x minus 1. Well, if you go back to the number 2, we already know that if the bottom degree is bigger than the top degree, we get this situation. This goes off to 0. So you can say that this is that same exact situation, so this just goes off to 0. So what you end up with is just plain old y equals x plus 3. You can just throw away the remainder. So then all you have to do now is graph that. So we have a y-intercept of 3, a slope of 1, and you draw a dotted line there. So you can see what the slope is for the slope of this line very quickly from the leading coefficients. That a over b is going to be your slope, so that's 1 over 1. So let's look at this in Desmos. So you can see here, this is our equation that I have created. We have 4x squared, but our top degree is bigger than the bottom. So we get this slant asymptote. Do you see the 4 over 2? Those were the leading terms, right? And so the leading coefficients are giving us the slope that we want. So this is 4 over 2. So it's going up 4 over 2 from that initial point of 8.5. So it's up 4 over 2. And that's it. That's all three, because there's only 3 situations, but you want to use synthetic division. And I'm just going to play with this to show you what I'm talking about. So if I change this to 2, see they're both the same now. We get 2 over 2, but the 2 in the front, they just give us the line. And that same idea will happen. You see how the line is approaching it? And so it gets closer and closer, but the same idea, if I scroll in, you can see there's a slight gap there. It's going to approach it. So as our graph, as our x goes off to infinity, our function will approach that horizontal or slant asymptote depending on how the degrees are related. So if the top degree is equal to the bottom, it's just the leading coefficients. You put y equals those two numbers and you draw the line. If the bottom degree is bigger than the top, then we know it's going to go off to 0. And so you put little dotted lines, and that is what our horizontal would be. And if the top is bigger than the bottom, then you want to divide it synthetically so that we can create that fraction, which will then go off to 0, leaving us with this, our equation of the line. So that last one, when you look at this, all this is, this line right here is this divided. So we take the 2x minus 3 and we divide it into the 2x squared plus 5x minus 2, and we get this equation with the remainder going off to 0. So here are some problems for you to try, and what I want you to do is to take them and try and find the horizontal or slant asymptote. That's it. Now I did throw one little trick in there for you, okay, but I'll explain it when we get there. So all I want you to do is first just find the horizontal and slant. So we'll do the first one together to show you what I'm talking about. So the top is bigger than the bottom. So we take x squared plus 0x plus 2, and we divide it by x minus 3. So this would be 3 into 1, 0, 2. Multiply and add. And remember, the remainder is our fraction, so that goes off to 0. So this just becomes y equals x minus 3. That's it. So again, change the sign. 1, 0, 2. Bring down the 1. That's 3. Bring down the 3 because you add them. 3 times 3 is 9. It's 11. Who cares what that is because it's a remainder. It's going to go off. So this would have been 11 over x minus 3. That goes to 0. So now you plot that line. 3 up 1 over 1. And you draw the dotted line. So if you were to graph this function, you would see our graph approaching. And you can even use the denominator as well to make your vertical asymptote. Right at 3, we have that other line. And so you're going to get those graphs in there. Let's do one more. So here the degrees are the same. So we have 1 and 1. These are nice and quick. It's just the coefficients. So it's y equals 1. And so you go to 1 on the y-axis and you draw that horizontal line. That's it. All right, so try these. There's 3 more for you. So I just want you to tell me what is the asymptote and then graph it. So hit pause now and try it. Okay, so these are the answers you should have gotten. You should have, and so you should say no asymptote. See, there's my tricky one I had to throw in there. So if you had said that it was a slant asymptote and you did the long division, you got x plus 4. That you would have noticed that. So 1, 0, negative 16, and by 4, you get 1, 4. That's 4, that's 16, it's 0. Right here should tell you, if there's no 0 here, this literally is x plus 4. It's not that it's an asymptote at this time. What it is actually the graph, and then up 1 over 1. It's a line. Our graph is a line, but what we do have is at 4, 8, we have a hole. So when you see this situation, it actually will give us a hole, and we'll talk more about that in the next video. So over here, though, you should have had y equals 0. So the whole idea is to make sure, just like I stated in the first video, to always factor your rational functions first. and then see what cancels. So this was y equals 0 because, again, the bottom is bigger than the top, so we go to 0. This one also, bottom was bigger than the top, you get y equals 0. So those two you should have got perfect. This one you should at least have a dotted line, which you can now draw in. So I want to show you in Desmos this one and why it works. So I've already plugged it in and it graphed a line. You notice there are no vertical or horizontal asymptotes here. Nothing. No verticals, no horizontal. What you're getting, though, is that hole. You see it? That's where it canceled. And so you can see that we have values here until we get to there, and then it says undefined. So it doesn't show up until you actually plug it in, and then it's back to normal. So it'll say undefined, and then back to normal. So all of these values are good except for this. So all this represents is a hole. So it's a way to put numbers in that you don't want to appear. That's our denominator there. But that's it. So those are our rational expressions for horizontal and slant asymptotes. So again, it's just the degree. If the degrees are the same, it's the coefficients. If the bottom is bigger than the top, or the top is smaller than the bottom, then it's 0. And you're going to get y equals 0. We would write that on there, y equals 0. And if the top is bigger than the bottom, you're going to get a slant asymptote. In this case, we're going to try and keep it always linear. So y equals x plus 3. That's it.